Okay, welcome everyone to our first talk seminar of this semester. Thanks go to Piotr and Alexandr for taking charge and organizing. Do either of you want to say anything else about that?
No.
Okay. Okay. Well, thanks to you. So now on to our speaker, Andoni is professor at Columbia. Before that, he was a researcher at Microsoft in Silicon Valley. He got his PhD from MIT, of course, working with Piotr. And he has done a lot of groundbreaking work, especially in nearest neighbor problems and high dimensional geometry. And today he will discuss a breakthrough in approximating at a distance. All right, and I will leave the floor to you now.
All right, thanks for the introduction, thanks for the invitation, and apologies for starting a little late. I didn't realize that the time has shifted since I was at MIT. We were lazier back then, right? Started a little late. So this is joint work with Negev Shekel-Nosatski, who's a student at Columbia University, and I'll talk about approximating at a distance in near linear time, and to cut the surprise, the approximation will be a constant. Okay, so let me start from the beginning. Quick introduction. I'm sure, especially in this audience, I don't need to introduce the problem. Many citations that I'll mention later are actually done by faculty and students here at MIT. Nonetheless, eddy distance, it is a very classic measure to measure distance between or similarity, dissimilarity between strings. In particular, one that models also kind of alignment issues. So in particular, formally, it is the minimal number of insertions, deletions, and substitutions to transform one string into the other. There's an example of banana and ananas, and here the distance is 2 because we can delete a letter B, introduce S, and we have 2. Okay, distance of 2. And I'll note this distance, I'll have a subscript n, just to denote the length of the strings, which we'll think about them as being n. This distance appears in kind of many settings, many applications. You can, immediately imagine things like bioinformatics, where, the strings that we're comparing are, for example, genetic codes of these fruits, or natural language processing, and many, many, many applications. Okay, this is, a definition that, is decades old. Okay, and I guess this is kind of one reason to study it, right? Another reason is that deeper in theoretical computer science, it is a classic example of dynamic programming question. Okay, so a classic algorithm from '74 runs in quadratic time, and it's a classic example of dynamic programming. Probably many of us are teaching it in Introduction to Algorithms. I'm definitely going to teach it in a few weeks from now. In my class, and basically build a two-dimensional array, which is n by n, and there is some recursive formula to fill this array with. You compute it, and in the bottom right corner you read off the answer. Okay, and the answer of what is the value of eddy distance between two strings. You can also kind of follow through what is the path that you got to that number 2. Which will kind of correspond to, from where you can decode basically which characters got inserted, deleted, or substituted, or, what is the alignment, what is the characters that kind of remained, got untouched. It's a classic problem, quadratic time, great, but, of course, nowadays, the strings are long and would like to do it much faster than quadratic time. This problem has been studied for decades. So, in a sense, we didn't even need kind of the notion of big data to, really know that we need to solve this problem faster. But fundamentally, it is also about just like one step kind of at a higher level. The question is, how can we speed up some dynamic programming questions? Right. So many dynamic programming questions would have runtime which is quadratic or polynomial in n, but not linear, which is something I would hope for. So the question is, how do we speed up these dynamic programming questions? And eddy distance is a very, very good example, kind of like prototypical a problem of this sort, which has been studied from this perspective. Okay, so what can we do? So really, kind of the best algorithm is basically from 1980s by Maciek Patterson, who improves his quadratic runtime by log squared time. Okay, so not much further from quadratic. The problem has been studied in many other special cases. Think, for example, when edit distance is actually small, so there are just a small number of edits, or average case, moved case. Think about some kind of pseudo-random kind of settings. And I'm sure I missed many references. I just included some, but it has been studied over decades by many researchers in slightly different communities, in fact. Okay, now recently work that has been done by faculty here, in particular Piotr and Ryan in Virginia, have proved an amazing result, saying that look, we don't really hope to get less than quadratic time unless you disprove something even harder to solve, the strong exponential time hypothesis, or even actually more valuable hypothesis than the Ceph hypothesis. And to me, this kind of lower bounds, or kind of indication of a lower bound, is one of the kind of jewels of this modern area of fine-grained complexity. This is what this FGC stands for. So basically saying that, okay, unlikely to get quadratic time, stop quadratic time. Okay, so what else can we do? And in some sense, even predicting really this fine-grained complexity result, it's natural to say that, well, can we maybe somehow approximate this this distance? Okay, computing the distance approximately, somewhat similar to, I guess, the progress that has been done for NP-hard problems, where a number of decades ago we said, like, well, those problems are NP-hard, we can't really solve them in polynomial time, but maybe we can do something better if we are to approximate the solution to the problem. Same here. Okay, and again, also, so this is really the work that has been done in the first decade of the century, and the culmination was really getting near linear time, so something like n to 1 plus order epsilon, and the approximation factor was polynomial in n. Okay, and I just realized that this first reference is also by an MIT professor, Ronit, and yeah. So that was that happened roughly in I guess first decade of the century. But then, about 2 years ago, there has been, breakthrough progress on approximating the distance in subquadratic time. In particular, there is, these two results are roughly, the same time, independent. One was quantum algorithm, and another was, kind of real classic algorithm, and both of them got approximation factor, which is a constant, in time, which is, strongly subquadratic. Okay, but looking at these results, it's natural to say, like, okay, how far can we push this type of techniques? Can we get near linear time? So not n to 1.6, but something closer to near linear, while still retaining a constant approximation factor. Or what is the kind of trade-off that we can obtain? Okay, and there has been some progress on this. There are a couple of papers this year that obtain near linear time, constant factor approximation. The approximation factor depends on epsilon, on the target epsilon. But there is kind of a big caveat in a sense, namely that the approximation that one obtains is not only a multiplicative constant factor approximation, but there is also an additive term. So something like n to 1 minus some function of epsilon, again, where epsilon is the one that is from the target runtime that you want, and basically means that, okay, if I want time which is n to 1.01, for example, then there'll be some additive factor which is very close to linear in n, which equivalently you can think about it is an okay approximation algorithm if your edit distance is relatively large, so close to linear in n. But if it is a little bit less than that, then it doesn't really give you anything. Okay, so natural question still remaining is can we get constant factor approximation in near linear time without this big additive caveat? And this is the result from today, basically. But yes, we can compute the distance in constant factor multiplicative approximation in time, which is n to 1 plus epsilon, and the approximation factor depends on epsilon somehow. I'll mention this at the end. So this is the statement of the result. There is not much more about from the introduction, but I want to say at this moment. I'll try to kind of delve into some details of the algorithm as much as possible from now on. So it is a good time to pause for a few seconds to ask if there are questions, perhaps. If not, I mean, feel free to ask me questions. Very much welcome the questions. And from now on, I'll basically start setting up a little bit things, and thereby I'll mention basically some of the details of the past work that obtain a constant factor approximation to the distance. And then, of course, I'll talk about our result.
So Alex, so I don't have a question, but I have an announcement, which maybe I should have made at the beginning. So the talk is recorded. So you know that, but now everybody else knows, right? So
I see. Okay, so be careful what you say, right?
What questions you asked.
Right, exactly. Okay, cool. So yes.
Sorry, I was just going to ask, are you going to tell us about the dependence of epsilon in the big O?
It's something like doubly exponential or something. Okay. No, really bad. So yeah, that's why I don't mention it, right? But okay. We can talk, last slide, we can talk about it, right?
All right.
Cool. So, all right. So let me just describe a little bit of setup, and I'll try to explain where it comes from. But the setup in a sense is common to a few works on eddy distance, definitely to these constant factor approximation algorithms. Okay, so kind of part number one is that, or observation one, perspective one is that eddy distance, computing eddy distance between two strings is basically equivalent to finding an optimal alignment between characters of one string and the other. Okay, so here is kind of illustration of it, right? We have a string x and y. These are n length strings from some alphabet, and these arrows correspond to this alignment. Not, as you can see from, the extra letters in bananas, right? Not all letters from one string will correspond to the other string, and so and the other way around. And these are the ones that don't participate in this optimal alignment are the ones that should be deleted or inserted in the other string. Okay, so in a sense, this optimal alignment corresponds to the characters that are not touched during the operations of eddy distance. And basically describing an optimal alignment is pretty much the same as describing this, the finding the value for eddy distance. Okay, so here is one thing that many of these works now do is basically consider substrings. Okay, substrings of length w. Okay, we'll call them capital Xi and capital Yj. These are substrings starting at position I and j of length w. You should think of w as being relatively large, something like n to 1 minus epsilon or root n if you want. Okay, and think about this, kind of jumping ahead is kind of, this will be kind of, some kind of recursion, right? We will recurse and try to reduce to computing eddy distance on strings of length w. Okay. Okay, so what can we say about splitting into these substrings? Well, one fact, kind of, right, or one useful fact for us will be that we can think about eddy distance between x and y as computing eddy distance between substrings in a sense. Okay, so this is just to kind of decode this formula really. It's minimum over, again, all the optimal alignments between x and y. And now we basically sum up of the cost of matching substring xi to the matching substring y. So it's the eddy distance now of substrings of length w, of substring xi versus substring y, starting at the corresponding match, basically pi I. Right, so for example, this substring will be matched, for example, to this substring. We have to normalize by w because, well, these strings are w and we're taking all substrings. So this is basically, we can describe eddy distance, computing eddy distance between two strings as computing some kind of optimal alignments between substrings of x to substrings of y. Okay, and this is kind of more formal way to state. Okay, and that's some fixed constant approximation. Okay, so given this fact, now the goal, which at the moment is not obviously simpler, is to say, well, instead of computing a optimal alignment between x and y, let's try to find a perhaps near optimal alignment pi between substrings xi and substrings yj of x corresponding and correspondingly y, while thinking somehow that we maybe have an oracle or some kind of black box that can compute any distance of strings of length w. Okay, this is this blue eddy distance of strings of length w. Okay, and I assume that you can see my mouse, right? Tell me if you don't. Yes. Okay. Thank you.
Yeah.
Cool. So, all right. So this is the goal. And okay, so why again these xi's are intervals of length w. Okay, so why switching this goal? At the moment it feels like a little bit harder actually. This is really, if you think about it, this is like computing a distance between strings which are still of the same length roughly n, but now our alphabet are strings of length w under some metric, even harder metric kind of, right? So so far we've just made it harder. Okay, so why should this help?
So Alex, can I ask a question? Vinod, in the previous slide, what does the approximate sign refer to?
Factor 4, I think, is provable.
Okay, I see. Okay, all right, thanks.
Oh, 2 maybe, right? I don't remember now exactly.
Okay, yeah.
Cool. So, all right. So here is, let me just, go from something, naive to, more interesting. So, the first thing, to do is kind of, okay, so how to do this naively? It's like, well, first of all, if we are, the moment focusing just purely on the kind of recursive calls, how many times do we need to compute the distance between shorter substrings? Okay, well, there are, n substrings of x, n substrings of y, in the worst case, we need to compute all pairs, these n squared calls to this EDW primitive. And this means, at the moment we don't know how to compute it, to compute the distance between strings of length w any faster than quadratic still. This means that, total time is, something like n squared w squared. And this is, much worse than we started with. Okay, so here is idea 0. And I mean, this idea, predates kind of, a lot of this work. Namely, well, there should be some win of us considering some strings. In particular, why don't we just consider start positions or substrings which start at whose start position is a multiple of w, right? So if you're really splitting into substrings, we shouldn't be taking perhaps overlapping substrings, and just take, for example, from x, just take, x1, xw, x2w, and so forth, right? So there are only n by w such substrings, which, again, w is relatively close to n, so, this is much smaller number of substrings. Okay, good. One issue is that, okay, we can do that, right? But then optimal alignment, so for example, x1 might be matching to something like y100, for example, right? Which is not a multiple of w, right? And the same here and so forth. So generally speaking, the matches, the corresponding matches, even of these integer start points, will not be multiples of w. So this means, that will be an error because we can't match to, our favorite substrings in a sense, to the right substrings. But one can do something here, at least, at the cost of an additive error. In particular, instead of, in let's say in the other string, in y, instead of taking all the, integer multiples of w, we'll take all the start positions which are integer multiples of delta w, right? And think of delta as being small constant or a little bit less. Okay, and then, all these optimal alignments, like this j, if you take this pi I, which is a multiple where I is multiple of w, take corresponding j, round it to delta w, and do it, for all possible i's, then, it's pretty simple to prove that, one can still kind of compute an approximation to any distance, but there will be an additive error of delta n, right, coming exactly from this rounding issue. Okay, so for example, maybe I should just raise that, know that this is one of the sources where additive error kind of naturally appears, right? Like where, why additive error, maybe a simpler problem than having no additive error. Okay, but okay, let's assume, let's go with a float at the moment, right? Assume the delta is small, and be okay with this additive error. Okay, so what do we buy? Well, what we have is that with the number of start positions in X is n by W, the same in Y for constant delta. This means that the number of pairs is now n by W squared, and let's say each of them, is computed again with some standard dynamic programming solution for strings of length W. Right, so this will be n by W squared, and each of them takes time W squared. The total time is still n squared. We still did not save time, even with this splitting up and rounding and stuff. Okay, okay. The one good part I should mention though is that what we did buy is that after we've computed all this, after we've computed all these pairwise, let's say, distances between substrings, right, starting at the right starting positions. The good part is that the total number of substrings that we need to care about is only n divided by W. So we can run a dynamic programming, kind of a modification of the standard dynamic programming on these substrings. And even if it runs in polynomial time, but this is still okay, right? I mean, this polynomial time really will be quadratic, but it will be n by W, which is n polynomial. And think about W as being, I don't know, even, n to 0.9 or something like that, right? So computing the optimal alignment at this moment is not an issue. Okay, the only issue remains is how many calls to this primitive of computing a distance between shorter substrings we have to do, and this is why the goal is really stated from the perspective of how many calls do we need to do this, right? Okay, so here comes the ideas, right? And these are pretty much the ideas that led to this first constant approximation algorithms. Okay, so idea number one is that is to use basically metric property of the edit distance. Okay, in particular, that edit distance on strings of length W is a metric. It satisfies triangle inequality, and this means that we can deduce values of edit distance on strings for which we don't directly run this oracle for shorter substrings. In particular, just to kind of give a super simple example, kind of, right? I mean, well, if you have let's say x1 and it is close to all the other substrings, and we have y1 and it is close to all the other substrings in y, and x1 happens to be close to y1, then we can deduce the same about all the other substrings, right? So this roughly kind of corresponds to a quadratic improvement, right? Rather than comparing all pairs, we just use triangle inequality to deduce a lot of but a lot of pairs are closer, are close. Okay, of course this needs us to guess who is close to whom to be able to actually compare them and certify, right? But principally at least, right, it should reduce the number of, let's say, these recursive calls from m squared to roughly near linear. So this is idea one. Idea two is, again, something kind of a little bit more specific to edit distance, perhaps, is the following idea that, let's say, some string x1, it matches to this y which starts here. Maybe it's y100. Okay. Well, if I look at xw, and the edit distance is relatively small, then this means that the start position, the corresponding start position, where xw should match, should start at the kind of proportionally, further away, right? So formally, if start position iw matches to position j, then the next substring starting at position I plus 1w should start roughly at j plus w, unless there are too many edit distance errors kind of happening exactly in that block. I mean, if it's not the case, then kind of the one start position, like one match, should predict where should the next match be. So at least on average, this kind of deduction should hold. Okay, so these are two ideas, and if you put kind of these two ideas in the right way, you already can improve on the quadratic time algorithm and get a little bit better. And in particular, basically this paper, this is the best paper award from best paper award paper from Fox 18 by Chakrabarty, Das, Goldenberg, Kutsky, and Sachs. This was the first standard algorithm for computing eddy distance in constant approximation, subquadratic time. What we really can show is that the number of such recursive calls to the eddy distance, to computing eddy distance on shorter strings, can be reduced to something like n by w to power 1.5. Okay, so remember, kind of n squared was kind of the idea zero, kind of adaptation of the naive algorithm. So we, in a sense, can reduce it a little bit to 1.5. And so the total time becomes n by w to 1.5. And let's say, even if we use kind of the standard dynamic programming for computing eddy distance on shorter substrings, which runs in time w squared, okay, then this is kind of the thing of computing. This is the time corresponding to computing with oracle calls to eddy distance of shorter substrings. Plus, the second term corresponds to actually finding the optimal alignment. It's n by w to some constant. And you can now optimize for w, and you'll get something which is a little bit less than quadratic. Okay, and you can also recurse, and then this will be w to 1.5 and so forth, right? I mean, it's something that will be close to n to 1.5, but not quite, but still. Okay, so these are the ideas. Now, the more recent papers show that you can reduce the number of these calls to something like n by w to 1.5, sorry, to 1 plus epsilon, right? So this is, much more promising in terms of, getting to near linear time. And, this is why we do get near linear time. But remember that, idea zero already gave an additive approximation just because we had to round the starting positions in Y. There is also an additional error term, roughly corresponding to the idea that, well, once I, kind of am allowing myself to have an additive approximation, then I actually can ignore, or in a sense fail to find a lot of the matches in this optimal alignment, right? So I can ignore, a slight, something like n to small function of epsilon, fraction of matches, I don't need to find, right? I mean, this will introduce some additive approximation, but that's okay. Kind of, right? We already have additive approximation. Okay, so this is, this is the prior stuff, right? And now I'll switch to talking about kind of, our ideas, or at least, some glimpses of it, I'd rather say. Are there any questions so far? So, there will be a few things. You'll see that idea 1 and idea 2 will also appear somewhat in our algorithm, in somewhat different form. But, they'll still be, there somewhere, and I'll try to pinpoint where, in a sense, these idea 1 and 2 are being used in our algorithm as well. Okay, but, some of the framework is a little bit different. Okay, and I'll start describing this framework unless there is a question. I guess not. Okay, so here is our approach, and this is the high level. And to think about this, this high level approach, bring in, kind of your, I guess, like metric geometry kind of hat, and really think about eddy distance as being a metric, and this will be like one perspective that we'll take up here, at least on this slide, for this part of the setup. So in some sense, we naturally use triangle inequality and the fact that eddy distance is a metric. So here's what we do, and in some sense, you can think about this as somewhat replacing this recursion that would happen in the previous algorithms. But what we really do is, instead of kind of having really, I mean, it's not really replacing recursion, because we'll see that, this allows us, to do more really. But it's, in some sense, it goes from bottom up. Okay, so what we'll do is we'll build, so for W, for strings of length 1, and then n to the epsilon, n to the epsilon to n, there are a constant number of steps, we'll build a distance oracle, which we'll call dW, for the entire metric of all the substrings of x and y under the eddy distance. Okay, so distance oracle is just a data structure, but given basically two strings, I mean identities of two strings, right? You say like, you know, substring of x starting at position 100 and substring of y starting at position 300. Tell me what is their eddy distance. Okay, and this data structure will do this relatively fast, right? I mean, we'll spit out the number and you know, that will be relatively fast, right? This is what distance oracle really mean, and you know, it corresponds to the, you know, standard notion of distance oracle, and this is on always two n substrings of strings x and y. Note that, you know, it will also answer distances between substrings of x or substrings of y, so x versus x, for example. And you know, we'll build this iteratively. So D1 corresponds to substrings of length 1. So this is really just characters. So it is really just Hamming distance on the original alphabet sigma. Okay, are the characters equal or not? Okay, so using D1, we'll build this, you know, distance oracle for substrings of length n epsilon and 2 epsilon and so forth until we get to distance oracle of all the substrings of length n, which means that, you know, we can just ask what is the, you know, distance between x1 and y1, which are of length n, which, yeah, it's exactly equal to the distance between x and y. Okay, the full distances. Now these distance oracles will be approximate, so, you know, therefore we'll get an approximation. Okay, and the approximation is roughly the following. So this is, you know, slightly more formal guarantee that these distance oracles give. In particular, for any substrings I and j, again, from this, you know, calligraphic IW, right, which corresponds to all substrings of x and y together, we have this inequality, right? This is some kind of, you know, approximation, but with one caveat that you'll see. One, it is always lower bounded by the actual eddy distance between I and j. Okay, so they can only overestimate the distance. And on the upper bound side, it is, think about, I mean, ideally would like, you know, to say that, well, this is upper bounded by some constant times the distance between strings ij. We cannot do that. But what we can do is basically we can have this upper bound hold again up to a constant and just enough places so that we can compute the eddy distance at the end. Okay, formally, a little bit more formally speaking, is that this upper bound will be up to a constant, but it will hold only on average and only for an optimal alignment pi. So when I is substring of x and j is the corresponding substring of y, okay, under this optimal alignment, which minimizes the eddy distance, and this, you know, the upper bound, this red upper bound, this squiggly inequality will hold only on average. Okay. And the distance oracle, you know, to output a number, you know, what is the distance between I and j will take time, which is n to order epsilon. So, you know, small from our perspective. Yes, there is a question.
Yeah, I do have a question. So, like, when you say average, like, do you literally mean on the average that if you
sum over all i's of this dw between xi and the corresponding string y pi of I.
Okay.
Yeah. Yeah, like, there will be another perspective on the same thing in a little bit again. So yeah. Okay, so, you know, now, you know, what needs to be described, right, and, you know, where all the action happens is how we implement one of these bluish arrows, right? In particular, given distance oracle for strings which are a little bit shorter, how to compute a distance oracle for a little bit longer strings in time which is nonlinear, n to 1 plus order epsilon. Okay, so this is what we'll focus now. We are given a distance oracle for strings of length w divided by n to the epsilon. We need distance oracle for strings of length w. Okay, so, you know, here, you know, the shorter, the less ripe strings are, you know, here, the less ripe data structure here, you know, the more ripe data structure on the right. And there are two components really. One is the following. So this is this will be another oracle, and it is really a kind of a wrap around the distance oracle. We call it ALW. I mean, it stands for alignment distance, and it is it's basically it's just an oracle and given INJ, it will use, it will implement some kind of dynamic programming, which will use Oracle calls to the distance Oracle on shorter substrings to compute the distance on slightly longer substrings. Okay, and we guarantee that it will have, so this is where going from shorter substrings to longer substrings happens. Okay, and somehow it kind of puts together substrings, implements some kind of dynamic programming. And again, we won't have guarantee that, the guarantees for these alignment distances, alignment distance will be roughly the same, but we'll want at the end of the day from the DW, from the distance Oracle on the longer substrings. As in the lower bound always holds, but the upper bound is again up to this squiggly inequality. Okay, computing given IJ, this takes n to the epsilon time to compute together, and the same amount of Oracle calls to the distance Oracle on shorter substrings. Okay, and think about this. This is dynamic programming. There are some details, but it's at the end of the day, it's a form of dynamic programming. Now this is where the second component comes, which we call matching algorithm. And basically it says, well, given an Oracle access to this alignment distance of strings of length W, we want to build the distance Oracle that doesn't have any, distance Oracle data structure will be by itself. It will not have any Oracle calls to anybody, right? So this is what we need to do. Okay, and the way we'll do is that first we'll build a graph. This will be, where the main kind of action happens. This is the actual matching algorithm. We'll build a graph whose shortest path distance on this graph will correspond to this alignment distance ALW. Okay, this is, formally, again, distance in, so this graph GW, again, it has two end nodes corresponding to all the substrings of X and Y. Okay, and if you take shortest path on in this graph, then again, a similar kind of approximation guarantee holds, right? It's lower bounded by the distance, upper bounded on average, for the right alignment or by the alignment distance. Okay, and the second part is, just kind of more classic things that many of you have seen before, and prove the results on. Namely, it's a distance Oracle data structure. So given a graph, we just really build standard data structure, which is a distance Oracle, and just outputs constant factor approximation to the distances in the graph GW. Okay, so in our perspective, you can think about this as this distance Oracle DW will be some kind of dimension reduced alignment distance metric, but is just captured by the data structure itself without having to call the Oracle on this alignment distance. There is one caveat, but why we can't use kind of standard or some of the standard data structures for distance oracles, namely that we want the DW that we output is a metric itself. Because remember, later on we'll again be using metricity and triangle inequalities, to do stuff. We don't want to lose that, and things like, for example, Torvalds Beak, as far as I know, won't have an output which is guaranteed to be a metric. So it's something which is, I guess, even more classic. Namely, it turns out that for us it will be enough to implement, let's say, Matuszek's embedding into L infinity. In particular, you take the shortest path metric on the graph, embed into L infinity of dimension n to the epsilon. This gives, order 1 over epsilon factor approximation, and that's enough for us. Okay, so the distance Oracle is really just, a bunch of vectors, and computing the distance between two things is just computing L infinity distance between two vectors, and that's all. Okay, so from now, yes, Piotr?
So quick question, right? So, I mean, it's not obvious that you can compute all these distances efficiently, right? And so, like, like you are putting lots of things under the carpet, right?
Right. So I'll talk a little bit on the next slide about this, right? But yes, I mean, just to address Piotr's question, indeed. So think about, what this matching algorithm, this arrow, right? And red matching algorithm, what it does, it takes, what it really does is like, okay, we have an oracle, right? So we have like a black box, right? Which captures some metric, AL and W on two endpoints, really, right? These are all the substrings of X and Y. And then we build a graph which captures all these distances, and we want this to be up to constant factor approximation. Now, this is, without doing precisely this is impossible in nonlinear time, because the amount of information captured by this distance is roughly n squared, basically like all pairs or of that order. There is no way we can do this in linear time by asking only near linear number of queries into this metric. So this is exactly kind of issue, and in some sense this is why our upper bound is always up to this squiggly, and it is on average for the optimal alignment only. So let me kind of move on to the next slide. I'll have a slightly different reformulation of this there, and maybe this will help a little bit. So think about this as, we don't approximate the entire metric for sure, but we approximate just enough so that at the end of the day we can compute the edge distance. So roughly this is just like, some theory version of just in time, I guess, right? All right, so let me focus on this step, right? And this is really, if you can, look through the paper later, this is really the step which is, by far where the heaviest of the lifting is happening. And let me focus on one scale, C. Right, so we want to, again, we have an oracle to this alignment distance, this some distance, which is some form of approximation of eddy distance on substrings of length W. You want to build a graph, so the shortest path distance in the graph is approximation to this distance, to this box, the box, and we focus on a scale C. And roughly, this is what kind of ideally what we'd hope for, right? So this is kind of the two directions. One is that, well, if there exists an edge in the graph, this corresponds, an edge in the graph would correspond only to strings ij, which are, maybe a constant factor more, so order of C. Okay. On the other hand, if this alignment distance is at most C, then there exists a, constant hop path in the graph. In our case, it would really be just two hop path, right? Corresponding roughly to triangle inequality. But this is ideally what we'd want, right? If we just care in a sense about one scale, right? I mean, all the distance either much smaller than this C or much larger than C. So this is what ideally would hope. Now, this is not possible exactly from, because of the discussion from the previous slide. This alignment distance kind of captures much. Sorry, it's not possible to do in nonlinear time because this alignment distance can capture, something like n squared information. So what really we want to do is say like, well, can we relax this, because at the end of the day, we just want to, find something for our optimal alignment. So we want to say that, well, the second property is guaranteed only for the right matches. So for any xi, and its match y pi of I, where pi is the optimal alignment. Okay, really, it should be for any alignment because we don't know what is optimal alignment until at the end of the day, kind of. So, so we really, should be able to say that this is for any alignment. Now, this is still not possible because if we have this guarantee and we say that this is for any alignment, that pretty much, forces this property, the second property, to hold for any pair xi and yj. And again, this is a little bit too much. So what we really do is that we'll do this for all i's except number of i's which are proportional to the error, where error is the number of i's where this distance is bigger than c. Okay, so this is really kind of the, at least in this case, this is a formal statement, right? This is what we can get if focusing on one scale. Okay, I know that in a sense, for any alignment, in a sense, it's most interesting for the optimal alignment, because for optimal alignment is the one that minimizes that error precisely, right? So if we're just taking an alignment which is, like particularly inefficient, then the error is very large, so it is much easier to implement this kind of desiderata. So it's really kind of, this statement makes most sense for the optimal alignment, which we, we don't know the algorithm construction kind of stage, but we'll know it. So it kind of goes in the analysis. Okay, and this can be done in nonlinear time. Okay, so time and calls to this alignment oracle. Okay, and let me introduce an assumption, which I'll call an ultra triangle inequality assumption. And in particular, this is what I already suggested when focusing on one scale, that either this alignment distance is much smaller than C, or otherwise it is much, much larger than C. Okay, in particular, there are things which are a distance 2C or 3C. Okay, and if this is the case, then we can really think about this, set of substrings, this calligraphic IW, as being composed of equivalence classes. Basically, two strings are in the same equivalence class if and only if there are distance at most C under this alignment distance. Okay, so below is basically a picture where it's a string of substrings which are coded by the capital letters now, right? So basically A's are not characters A, but substrings which come from equivalence class called A. And basically, between any two different instances of capital A, the distance is at most C. Okay, and the grade arrows, double arrows, corresponds to optimal alignment, which again we don't know at the at the stage when this matching algorithm is running. And the red characters are the ones which are in some sense error, right? They maybe they're in error, or they match to some substring which is a distance much more than C. Okay, maybe I'm at the moment I'm slightly confused. When should I end, or what is the schedule?
Yeah, so we started at 4:10. So yeah, I think we probably should finish in about 10 to 15 minutes.
Okay.
Yeah.
Okay, that's better than I thought, actually. So, yeah. Cool. Okay, so this is the assumption that we'll take, and I should yes. So first of all, this means that what it really means in this situation, that the goal becomes to identify these classes, right? As in, again, if we were to build kind of a perfect graph that exactly captures this metric AL, under this assumption, this ultra assumption, then the graph would become a set of clicks, basically. Now, where a set of, to be precise, a set of connected components, each connected component corresponding to an equivalence class, and the diameter of every connected component is at most 2, right? Mostly because we allow these 2 hop paths for any pair which is considered close. Okay, but there will be some errors because of the errors coming from this optimal alignment. Okay, so right, so this is the assumption, and I should mention that this assumption is a big simplification. As in, I'll describe some ideas, kind of assuming this assumption. Not much. I'll just give a glimpse, right? But because of this assumption is so big that we can't really use the same ideas or reduce to it, right? And I'll talk a little bit about that later. But I should mention that this is not just a small assumption that we can fix later. This assumption, not having this assumption will force us to make many more changes to the algorithm than the problem is there at the beginning. Okay, so still, right? I mean, this let us see something. So here is kind of the main.
That's a question.
Yes, please.
So can you say a bit about why it's enough to build a graph for one scale? Or are you going to have like exponentially increasing scales? Or
yes, yeah, you can take exponential. Yeah, your scales are all powers of 2, and you just union them with the right weights, and yeah, that will be it, right? And you can check that this. Even this definition of the error will be just enough, kind of, right? That right, that the amount of error that we introduce for at each scale will be proportional, right? And kind of at the end of the day, something that introduces a certain amount of error, will the amount of error that we'll introduce will be proportional, right? But C is all powers of 2 here. Okay, that will be enough. Okay, So here's the main loop, and in a sense, what we'll want to do is to partition basically these substrings. Yeah, again, right? We have 2n of them, n for each string, and we'll try to do partition. This proceeds in roughly 1/epsilon steps. So in a sense, we'll have some partition pi0, then pi1, and so forth. Each of these steps introduces some constant error. Yeah. So constant error means we lose a bunch of these matches that should exist. We lose a bunch of them, proportional to the error so far, kind of. But all the number of steps is constant, so that's fine, kind of. But yeah, you can already see that this already gives at least exponential in 1/epsilon approximation, because each time we do this step, kind of the error kind of doubles, for example, at least. Okay, so we'll be building a partition pi t, and it will be something like n to epsilon parts, right? So we kind of refine partitions. We don't really do refinement, but you can think about building partitions which are finer and finer. So to build a new part, kind of in our current build partition pi t, we sample a bunch of anchors. So for each new part, we sample an anchor called A. Okay, let's say this is an anchor. This letter A, this substring of X is our anchor, and all the I guess black or red characters are things which are currently in the same partition with this anchor A. Okay, what we do is, well, we take A and we compare to all the ones in the current part, in its current part, which is defined by the previous partition, and we computed distance using this alignment oracle. Okay, and we get a set which we call E of A, which are all the equivalent substrings. So basically, these are all the substrings that distance at most C, or basically in the setup so far, these are all the other characters A which are not grayed out, basically. Right, so this is, this will be the set of E of A, right? These are all the equivalent strings. And note that, in a sense, why we're doing this, like, well, these are exactly the ones to which we want to connect an edge, right? This should be in the same part. And note that the set E of A can be quite large, for example, potentially as linear in n, kind of, right? I mean, that's the extreme case, but still. And what we'll do is, well, we'll build basically the graph corresponding to this cluster kind of A's which are close together will be a star, right? So we'll have this blue thing connect to all the red things, and all the others will be at at 2 hops away from each other in the graph. It's so kind of close in our definition. Okay, so I mean, this is good, but the thing is, most likely the number of this set E of A will be much smaller than the target part size, right? And this is, this will be no good for us. So what we'll do is that, I mean, this anchor will really be like a seed, in a sense, to build a part. Okay, and in a sense, what we'll be doing is that we have a target part size that we want to build, right? So this is n divided by number of parts. We'll want these parts to be relatively balanced, so this means that each of these basically red arrow friends or equivalent substrings will have some given capacity, kind of some responsibility in a sense of how much they need to contribute to the part, right, to the build part, right, which is corresponding to this anchor, right, and it will be roughly the target part size, whatever that number is, divided by how many we are, right? So equal responsibility for each of them. Okay, so what happens next? Okay, and this is just copying from here, and just for this, for illustrating this slide, I'll choose a slightly different anchor. Namely, this anchor will be this letter B. Okay, and right. So what we want to do is that what we call proximal extension. Okay, and what this proximal extension say, like, well, this, there are a few letters B. They need to capture something around them. We need to contribute certain amount of substrings to get part. Okay, so it's normal to basically to say, well, let's take things which are nearby this B, and this roughly, I mean, this idea roughly corresponds to the second idea that I mentioned from the previous approaches, right? Where if one substring matches somewhere here, then the next substring in X should match somehow the next substring in Y as well, at least on average. Okay, so the same here, right? If we manage, to have our anchor to be kind of, good, bona fide kind of match, then the things nearby around this B should be matching to things nearby around this B in string Y. Okay, so we'll basically, try to do this. But we have to be careful. In particular, what we'll do, instead of just capturing some some ball of some interval of or segment of radius R around each of these intervals I, we'll do something slightly differently. Namely, we'll take this credit, right, or in some sense responsibility of I, and distribute it to the nearby J's, right? So this is the nearby J's that are distributed. This is some radius, some form of R, and this gives some number for every interval J. Okay, so every interval J, in particular, all J's around here will get non-zero number with psi. Everything completely outside will be 0. Okay, and what we'll do next, and again, this is a very high level, right? I'm skipping too many details kind of at this moment, right? But I just want to focus on kind of a core idea. What we can do is the following. We can consider, rather than kind of committing right from beginning with an anchor kind of distributed responsibility to its friends, right? And these friends take something around them. Rather than doing this, basically, the friends are kind of, giving, maybe kind of ballot boxes, right? Like giving some kind of pamphlets to these J's, right? Which are called this psi. Now, each J kind of, at the end of the day, we've done this for a bunch of anchors. Now, each J kind of sits and waits until the process is done before deciding which part they go to. They collect all the kind of pamphlets that they got from all the anchors. This is some vector of positive numbers. And then the partition is done using min hash. Okay, in particular with a min hash, which views this as a weighted set, and basically each we pick one fixed random min hash function h for weighted sets, and a substring J is assigned to the hash corresponding to this weighted set. Okay, and roughly speaking, one can prove that the probability that two strings, substrings xi, and its match substring y pi I in the other string, if we look, what is the probability that they are separated? This will roughly correspond to the L1 distance between these psi vectors, right? These are things like these are collected vectors, obtained through this proximal extension kind of process, and the amount of this L1 distance will roughly correspond to the local error. Okay, so this means that the average probability, where average is over I, will be roughly proportional to the average of the local error, which intuitively corresponds to the total error. Okay, this is why, in a sense, at the end of the day, the number of pairs xi and its match that will be separated on average will be proportional to the the total error, right? Namely eddy distance in the entire string. Okay, now but yeah, if under that ultra assumption, this can be proven, right? As in there was a version of our manuscript where we actually wrote down this proof under ultra assumption, and you can push this through and get a result assuming the ultra assumption. There are more details here. In particular, what is the value of R really? And turns out that this entire thing is yet another loop where we basically repeat this for different values of R, and in some sense, this will be called levels, and different levels take care of intervals of different densities. You'll see like one of the biggest issue here is that some strings have many fans, right? Have a big set E of A, and some will have small, and that kind of affects things. This is where lots of the hardness kind of in the analysis comes from. So in some sense, these levels take intervals of the progressively less dense things, as in things with biggest density are taken care of first, and so forth. And there are other things that you need to threshold certain things, because otherwise, these vectors, for example, become kind of, if they are not sparse, then that's a problem too, kind of. Just holding this information, even though at the end of the day we'll assign kind of things well, if we need to store all these and they are non-sparse vectors, then there's just too much space to even store. Okay, and other details. So so let me not go further into kind of this construction, but just basically kind of highlight the main kind of conceptual kind of idea happening here is that the intervals are somehow partitioned. There's some kind of randomized process, and the way it is done is depending not on their value and who are they close to, but what happens to their neighbors as well. Okay, so their partitioning, how they're partitioned depends a lot on how their neighbors behave and how many friends they have and so forth. Okay, so just half a slide, or I guess one slide on beyond this ultra assumption. As I said, the big challenge is that we can't really reduce to this assumption. In particular, because this ultra assumption is a little too strong. It kind of says like either things are close or they are far, and somehow we need to have this separation kind of, right? I mean, things close versus far. And, at least the standard things that we know of, right? I mean, don't really work, things like taking a random cut of C or FRT-like metric decompositions, they don't seem to work because, they'll somehow partition, things in equivalence classes, but the probability that a right pair remains together is something like n2 minus epsilon, which is good in many applications, but not good enough for us, because this means that most pairs are actually separated. This means that the total error, in some sense, via the distance, is n. Okay, so then our error, additional error for this process will be proportional to the existing error. So this means that it will suddenly add, linear in an error, which is too much. And somehow, again, philosophically, this is, the issue is that we need a for all guarantee that, most pairs are together kind of most of the time, as opposed to for each, which is, this kind of guarantee that each pair remains together with some non-trivial probability. Okay, and the way to kind of we solve this with I guess much more work is that another principle is just to smooth off everything, right? This is very kind of umbrella term, right? But for example, we don't really have partitions, regular partitions. What we have, we call them colorings, and think about them kind of logically fractional partitions, as an interval is actually logically split between different parts, and it progresses through that correspondingly. Of course, the challenge is that once we have an interval belong to many parts, there's the sparsity things that we don't want an interval belong to n parts, because overall we have kind of n squared information to keep around, which we can't really do in near linear time. So there is a lot of kind of right kind of thresholding happening to make sure that things are sparse to be able to deal with them in near linear time. And kind of just our comment that, what is really this Jacquard or, weighted mean hash replaced with, even in terms of distance, in some sense, really what we needed there is the L1 distance between these vectors. So we replace this, again, in the analysis with what we call distortion resilient L1. So basically we define a distance, distortion resilient distance dd, up to some factor f, which basically computes the L1 distance, but only for coordinates which are sufficiently different. So coordinates where the difference is by a factor more than n to the epsilon. Okay, again, this appears mostly in the analysis. Okay, so, this is the final slide. This is, we can compute the distance in constant approximation in linear time. This is the main result. As I mentioned before, the approximation is doubly exponential in 1 over epsilon. Definitely not clear, kind of, at least in our algorithm, how to improve substantially over that, which leads immediately to kind of a very natural operant question that it feels given the type of tools that we're using, think about kind of standard trade-offs in distance oracles that one obtains, or the distortion, dimension reduction for infinity. There, the type of trade-off that one obtains is that dimension is, or size or query time is n to the epsilon, the approximation which is roughly 2 by epsilon. Okay, it's much more concrete kind of trade-offs, right? I won't get into there, but it feels natural to try to shoot for order 1 over epsilon approximation, or at least poly 1 over epsilon approximation, which will be doubly exponential improvement over what we have at the moment. So that's one kind of natural open question. The other kind of related open questions is, what can we, to shift a little bit kind of, how to view the question is to say, okay, let me try to get the best possible approximation in subquadratic time. What is that approximation? And, fixing that approximation, what is the best runtime, right? So first, somehow somewhat similar to how distance oracles, start at approximation, multiplicative approximation 3. Same here. The best near linear time, the best subquadratic time that we can obtain for some constant approximation is approximation 3 plus epsilon. For some reason, n to 1.5 would be natural, but we still can't even get that. The current best is n to 1.6. Of course, natural question, can we get less than 3 approximation? And that in some sense would mean going beyond using triangle inequality. There is a result that shows that you can get less than 3 approximation, but in the case when eddy distance is very close to n. Okay, something like 0.2n, then you can actually get a little bit less than 3 approximation. And of course, there are many other eddy distance problems, or problems where eddy distance kind of is featured. Let's say pattern matching, right? We have a text and a pattern. You need to compute the distance from the pattern to every substring of the text. Some of these tools can be applied for that problem as well, but there are other questions, especially related to nearest neighbor search, where the approximation factor is very, very far away from a constant, and it would be very nice to improve that. And I'll finish here. Thank you.
Thank you. Clapping. All right. Well, that's some very advanced stringology. Any questions, Alexandr?
Yes, I think that there were quite a few questions during the talk. So I don't know if there are any questions left. I mean, I have one of those undefined questions, right? Like, do you think that the right answer is indeed polynomial in 1 over epsilon approximation, or there is some hardness evidence?
Excuse me. Have you ever tried to use your methodologies to things like pattern recognition, image processing? Pattern recognition.
Well, I mean,
yeah. So let's do questions one by one. Okay. So, yeah. So Alex, you can answer them in any order.
But sorry, at the moment, like kind of one question raised the other. So
oh, I see. Yes. Yes.
1 over epsilon. I personally didn't see, evidence of hardness. Yeah, not clear. Not clear. Like the algorithm, I should say the algorithm is, becomes very convoluted. And there are many kind of, there are 3 levels of, there are 3 loops, one inside each other. And each step introduces constant factor approximation, but kind of, where basically squares the error sometimes, the factor. And, that's, I think, kind of the first question would be, to get a simpler algorithm, to be honest, right? Even before getting polynomial 1 over epsilon, right? As in, yeah. After seeing the Fox 18 result, right, I felt like, there should be a simpler algorithm. And, I think I got, some algorithm, this is this A18 reference, right? That is a little bit simpler to at least, get some, 3 plus epsilon approximation. But, getting new linear, things become very kind of convoluted that, yeah, it feels hard, but, not because I see kind of any evidence of hardness, but because just the current algorithm is so convoluted that it's hard to see kind of through all that kind of at the same time.
I see. All right, makes sense. And I think the second question was connections to pattern recognition, right?
Yes, or classification. Classification, yes.
Well, it depends exactly what you mean by classification, as in, this is an algorithm basically to measure similarity or dissimilarity between two strings. Okay.
How about two photos, for example?
Sorry?
Faces. How about two faces, two fingers, for example?
Yeah, I'm just thinking how to answer the question. So first of all, this is not really specific to computing the kind of the distance between images, right? It's more about strings or time series. Whereas I believe or think there could be kind of two-dimensional variants of edit distance for faces or fingerprints, but I know that for those kind of for images there are other measures of similarity which are more specific and are commonly used in, let's say, image processing, things like earth mover distance, and computing earth mover distance between two two images, for example, right, two-dimensional images is a problem kind of similar style where at least at the beginning kind of we didn't know how to do this in nonlinear time, and there's like higher polynomial time, and there has been work on trying to improve this runtime, including by researchers at MIT, and it kind of at a very high level, kind of it's a similar problem. We have polynomial time algorithm, but we want to do it faster. But when going kind of into a little bit more details, the type of techniques that go there are a little bit different than the type of techniques that go here.
Okay, thank you. Thank you.
Sure. But has been studied, yeah.
All right, shall we thank you one more time? Clap.
All right, thank you, yeah.
Thanks, Alex.
Thanks for the excellent.
Yeah, thanks. Yeah, thanks for inviting me. Yeah, happy to give a talk. Happy always to visit MIT, even if virtually.
Yeah.
Well, hopefully after the apocalypse is over, we'll be able to invite you again, right? But it's not happening for the next few months. So
okay,
thanks a lot.
Located. Where are you located?
Oh, I'm at home. I'm actually, incidentally, I don't live in the city.
You just noticed.
Like most of my colleagues, yeah. So I have actual trees behind me. Yeah.
Yeah, I was wondering if they are fake or.
No, it's like the type of background, like people put.
Camped out in the middle of Central Park or something.
You're at Columbia University now? Are you at Columbia?
No. I am outside Columbia. I live in suburbs.
Oh, okay.
Yeah. Unusual actually for Columbia faculty, at least in our department. But yeah, just personal reasons. Yeah, to live in suburbia, which yeah somehow now is came up useful, kind of unusually in a sense. So at least my kid can run in a yard. Cool.
Cool. All right. Thanks.
Right.
Thanks, Alex.
Yeah,
thanks a lot.
thanks.
It was great.
See you.
Thanks so much.
Bye.
Thank you very much.
We appreciate it.
Speaking out tonight about that awfully close call. The eye-opener's dead man has more. Go away. No, for sale.